So where we left off is on topic two. So you have a few examples here, as I mentioned previously. So please try to work out the example. Try to even though the answer is given to you, try to use your calculator and press on it, so that if you cannot get the answer, then please let me know so that maybe I can show it to you how you can get the answer lah, how to press the answer using your calculator. So this one is a bit on MS lah, but don't worry about the complexity of it. So the complexity and or the standard of question won't go very far lah from what you'll be seeing in your example and your tutorial. Okay, so coming back to your continuing on your lecture. So we know that sound is a movement of energy. So it's just a transfer of energy. Therefore, they can travel from point A to point B. So based on that, as they travel, they actually lose energy. So the energy of what they have is constant, but as they move further and further away, they lose their energy. So the energy is spread over an area, and then at a further away distance from the point source, the amount of energy for the sound actually decreases. So this is what it means. And then with that, we can actually come up with an expression or a relationship, which is this formula. So we have I, which is sound intensity, is actually 1 over d squared. So this is very similar to what you have in your chapter 1, which is your lighting. So the principle of the fundamental behind lighting and energy is very, very similar in a sense that as they move further and further away, their amount of energy decreases. So that's why the formula that they use is very, very similar. And then besides that, you also have another formula lah. So this is based on the ratio of any two intensity given by the formula. So at any different point of distance, there will be a different point of intensity, and this is proportionate to each other. So in light, you have your inverse square law. In sound, this law is also applied. But in the in respect to sound, then you have different value. So in the measurement in sound is based on dB. So dB is actually based on logarithm. So it's a way to measure very, very big and very small number value in a very general value. Because sound, when you are trying to measure it, there's actually a very wide range spectrum of value. So from a pin drop, where the value is very small, to the sound of airplane, which the sound is very, very big, the value will be very, very big. So to make sense of all these big and very, very big value and very small value, this is where logarithm comes into play for the measurement of sound. So, let's see. Hopefully you can find a scale, a graph scale. So logarithm is actually to the power of 10, meaning at very low value, then the range of value is real. Then when it goes to very, very big range or scale, then logarithm is able to simplify this value. So because the range of sound, the value range of sound is actually have a very, very big differences, meaning a pin drop and an airplane, they have a very, very big value of differences. But because we do not want to mention all these number, so we can actually simplify it using logarithm. So this is the idea behind why we're using logarithm or decibel as a scale of measurement for sound. So when it comes to the difference between 1 to 2 dB as mentioned previously in this table, we won't be able to differentiate it. So when it comes to point of source at 100 to 200, it actually says that as the distance increases up to double, there's actually a decrease of sound energy of at least a quarter. So this is very similar to what you have from your lighting topic because of the inverse square law. So this is applied lah. It's the same principle behind sound and the same principle behind lighting. All of them are related to each other. So as the distance increases by double, then only 1/4 of the energy is remain from the original. Okay, so just example 5 to showcase that. So example 5 will be able to showcase the idea behind this formula and also the changes or the difference between the decibel. So you're given a microphone measuring the sound at a position in a free field of 5 meter from point source, and then you have to calculate what is the change in the SIL if the microphone is moved to a position of 10 meter from the source. So this microphone is something like the sound measuring system, which sound level meter, which is this. So you have something that can measure sound. For example, here, so you have up to 5 meter here. At first they put here, they measured, and then they put another double distance, 10 meter, they put it here. Using in the same scenario, so they have to measure the difference between point A here and point B here. So given that you want to make use of the formula to find out what is the changes in the sound intensity level when we move it from 5 meter to 10 meter. So you're not given any value, but you're just given the distance. So making use of the formula, which is L, this is SIL equals to 10 log I1 over I2. So this formula is here, sound intensity level. So hopefully you still remember it. So for those, for the student who's new, you have to go back and work on it lah, see the video. But this formula, you don't have to remember it. So it will be given to you in a formula sheet, just so you know lah. Okay, so this is the same formula, but then everything is the same. For this example, you want to just minus and find out what is the difference. So you have this and this. So simplifying them, you'll be able to get that 10 log d squared 2 over d squared 1. So d squared 2 is a distance for the further one, and then d squared 1 is a distance of the original position. So this is using the logarithm rule lah. So hopefully you still remember logarithm rules of logarithm. And you'll be able to simplify the equation to something like this. And then once you compute the equation, 10 to the power of 2 over 5 to the power of 2, and you get this value, and you compute it, you will end up with the difference between the distance from 5 meter to 10 meter to be 6 decibel. So although I saying it just like this, it seems very simple. You have to apply the rules of logarithm to simplify the formula, plug in the value. Please do use your calculator to try to press through this, all these value lah. See that you can end up with 6 decibel. So if you cannot get it, then when there are free time, please ask me lah, so that I can show it to you. Okay. Okay, so this shows that when there's a difference between the distance when the distance between the original position and the new position is doubled, there's actually a change in 6 decibels. So let's say if the original intensity level measured is 90, when you increase the distance to double, regardless of how big it is, maybe it's 50 meters, you go to 100 meters, then you have to work it out. So maybe you should get the same result that the decibel is 6 dB. Okay, so next. So sound, as we know, it can be very pleasant, it can be very unpleasant, meaning it's unwanted. So due to us being unable to switch off our hearing ability, meaning we will always be able to hear sound, then we will want to make sure that the sound that we are hearing is only at the right time. Or we can design a area or a room where there's no additional noise. So any sound, if it's even if it's very pleasant to everyone, it will become a nuisance if it's happened during the time that you want to sleep. So some people will be able to sleep through it, but some people will not. So to not allow to make sure that there's no sound, that's why you want to study on this subject lah. So we actually learn. Actually, now we are learning regarding the fundamental of noise. So how to do a bit of the calculation. What is noise all about? Which is based on this, how we are able to perceive noise, and then ultimately we will come to the effect of how noise can affect us. And then at the end of it, we will talk about how or what sort of material that we can include in the building to work out how to reduce noise and how the material in our building can help reduce the level of noises. So when it comes to noise or sound that is very, very unpleasant, there are 5 factors behind the detrimental effects of it. So we can have hearing loss, we can have quality of life, and then we can have any interference, distraction, and expenses. So depending on what sort of condition that we want to set up for the place, if it's a workplace, then there will be hearing loss if we have a lot of noise in that area. So when it comes to construction, we actually have a lot of machinery all around. So this sort of machinery, they're actually exhibiting noise at a very, very high level. So that's why when we go to site, maybe we will need to wear earplug. So in your experiment, if you were to do it face to face, then you actually need to wear earplug for one of the experiment, which is the experiment 3. So you'll be briefed on that by the lecturer in charge or by me on that. Okay, so on other factors, so depending on where or depending on the situation, meaning where we are experiencing the noise, then we can have different factors that can affect us. Either if you're in a house and then there's a construction next door, then that will affect our quality of life. Or if you are trying to work, then there's noise beside us, then it's a distraction or interference. And then finally, if when it comes to business, so it's a commercial place, you're doing a business and there's noise, excessive noise at your area. So this will actually drive your customer away. So these are the few factors that is a detrimental effect of noise in our everyday life. So noise doesn't just affect us in terms of our normal life, but it can also affect businesses, our personal well-being, and also affect our work productivity. So it's not very good lah to have noise everywhere. So usually noise will come from construction site, or if you're living near the airport, I think you guys can hear a lot of airplane lah during my lecture. Okay. Okay, so when it comes to measurement of sound, usually this will be at site lah if it's required. So when you have a very big project or very commercial project, then you will involve the Department of Environmental. So they will actually want you to compile a report lah. So usually you will set up this sound level meter, and this sound level meter will be able to measure out how noisy your activity is. So when it comes to construction at the site, usually when DOA instruct to give an environmental report, meaning they want to know, is your site noisy? Is your site clean? Meaning, are you throwing uh, your wastewater or your construction water into the river? Then this is a sort of report lah, the DOE one. So construction just doesn't mean just involved with a client, architect, consultant, but actually there's many parties involved. So they want you to monitor the environment. If you have resident beside, then definitely they will want you to do a report, or the council, maybe the KL council or the MPBJ, they want you to do a report, or they will limit the activity behind your behind the hour of your construction site. So a lot of variable factors will affect the livelihood of people around if your construction site is near them. So one of the way to measure noise is this lah. Usually they'll just set this sound level meter up for a day or two and measure the sound from during working hours and compile the report. So how this works? So this is a electronic equipment. So therefore, the principle behind how this sound level meter works is they measure it through the variation of air pressure, voltage, and then they amplify it. So when they amplify it, it'll be in terms of value lah, in decibel. So what we see, what we know is we will get a value behind it, and then you will record that value. So this device shown is just a very basic device, meaning you will have to manually record it. There will be better device which is able to record it over a period of time, let's say 5 minutes, for maybe within 5 hours. So there will be a lot of reading, and you'll be able to compile a report for environmental. Okay, so as we have studied all these building services, so this is actually relatable towards site. So when we are working at site, there will be a lot of noise generated from equipment, electric equipment or mechanical equipment, to very big machinery. So this can be very annoying to people off-site, or people who live nearby the site, residential building or commercial building, or even people within the site itself. So there's a very big risk lah. And behind that, we have all these clauses and then also laws and regulation behind all this control. So we can have a factory and mechanical regulation. This is a very old regulation on noise control. And then we can have any limitation applied by the local council, meaning DBKL or MPPJ. So depending on where you do your construction at site, then they can impose on the limitation of when you can work and when you cannot work. So for example, if you're working nearby residential building, then they might limit you to a 5 days working hour. So you can only work from Monday to Friday, because Saturday and Sunday is the rest of people. So just so you guys know, for construction activity, we can go. It can be a it can be a very continuous process, meaning at site, if required, we can go and continue for 24 hours a day. So what I mean is that site activity, if there's no limitation, we can go overdrive, meaning we work 24 hours a day, 7 days a week. So definitely not with the same amount of people. There will be a rotation. So we have two shifts, each working 12 hours a day. And then they might be alternative, meaning you have different people coming in on Sunday and the alternate Sunday. So this is how a construction activity is when it's at the critical stage, or if it's just the nature or if it's already arranged to be worked 24 hours a day. Okay, so besides that, regarding this regulation, so this regulation is pretty standard when anyone who is working on machinery, either if it's on site or if it's a manufacturing plant, so this is not just limited to construction. So it's also applied to any industry that works with factory and machinery. So in order to protect or for the benefit of the normal people working or the employee working, we must not have more than 90 decibel. So this is actually to protect our hearing. And then if there's more than 115, then nobody's allowed to be exposed more than that level, or even 140 lah. So if you are being exposed to a continuous level of 90 decibel, then there will be a set limit of working hour, meaning you can only work in that sort of level of noise for 3 to 4 hours. That will be depending on the regulation that's applied. So whenever we are involved with all of different sort of activity, this uh, this sort of law will be applied So usually when it comes to construction at a very commercial stage, if you have any activity that deals with noises, then in construction it won't be for a very long period of time and usually you'll be provided with, by right you should be provided with hearing earplug. So always ask for an earplug if you're going to be exposed to very high noise level. Okay, so in noise in construction activity, there's actually 8 stages or 8 actions that we can use to control noises. So we can control it during the design and preliminary stage. Any choice of new equipment. So we can use new equipment. And then our work planning, work practices, distance and location. If we cannot do anything behind it, then we can go and rent the acoustic screen or barrier. And then finally, at the most basic level, we have your personal protective equipment, which is a PPE can have earplug or earmuff. So usually this will all be applied in stages. Whenever there is a noise in the construction industry or any factory, usually it will be planned out and arranged in a way that we do not bother other people. So if you bother other people and you and a complaint is reported, then either the council can come and stop the work. So construction industry is very vulnerable to that So the local council is the one who approve the work, and if people report a complaint or lodge a complaint to the local council, then the local council can come and find out what's the problem lah. So usually when they come down and they found out that if there's an excessive amount of noise or if there's pollution or if they are working off the working hour allowable, then usually what they will do is they will find the site. So if you are living around all these or living around construction site, so you'll find that if they are being a nuisance, not during the working hour lah, outside the working hour, or if they are being excessively a nuisance during their off working hour, then you can always report to the local council. Then they will come and do something about all this problem. So you're not helpless in a sense that you cannot do anything when it comes to construction site, even if you are just a normal person, not in the industry. Okay, so we can have a earplug here, ear muff. So usually when it comes to construction site, you'll mostly be giving a earplug lah. So example of how noise can be reduced when it comes to construction is instead of having a lot of activity on site, we can always go for prefab. We can put a acoustic screen behind any activity. So if you have a machinery that's moving, we can put a acoustic screen in the direction of the place where we want to reduce the sound. And then we have this. Okay, so I think this is the active noise reduction. So nowadays we have earplug or ear muff, which if you wear, there's actually a circuit in the earplug itself that's able to cancel off noises. So this is something new lah. So usually you won't encounter this equipment lah. You have to buy it yourself because if you lose it, then it'll be very expensive. Usually what's provided at site will be earplug, one-off use earplug, meaning once you wear, by the end of the day or after your break, you throw it away. Okay, there's actually two ways in which noise can be transferred. So one of the way is airborne, which is how your speaker, how your radio, or how your TV travels for the sound. And then the next is impact generated sound, meaning something is hitting on it. So these are the two types of sound that can be generated. So we can have airborne and we can have impact, meaning something or some activity is being done and sound is being generated due to that action. So that's what called impact lah. So when it comes to noise transfer, if it's a airborne sound, then you have to travel through the air and then you have to go through the building material. But if it's an impact, then it will be a direct force to your building. So usually what we experience everywhere will be airborne sound. And then even if it's an impact sound, it won't be impacting directly at the building lah. But then the level of sound generated will be very, very high, or it'll be a very loud sound when it comes from impact generated sound. Okay, so we have your sound insulation. So there's two ways we can implement sound insulation. So we can absorb it or we can insulate it. So both are different way of sound insulation. So when it comes to sound absorption, meaning we can absorb it in the surface itself. And then when it comes to sound insulation, then we want to be able to reduce the sound energy transmitted in the space. So both are different ways of insulating. Okay, we have a table here. When it comes to S, uh, when it comes to sound reduction, we call it as a SRI, sound reduction index. So different ways of configuration, you have a different level of reduction. So when required, this when it comes to example, this table will be given to you or as required lah. So you don't have to memorize anything. You just need to understand the concept behind it. So you'll notice that depending on the configuration, we have three types of configuration here. So the first configuration is for a wall which have a cavity and a brick. So this means that there's a brick layer, and then there's a cavity layer, and then there's another brick layer, meaning it's a triple layer wall. And then after that, they have plastered, and there's some wire ties. So with this sort of configuration, the wall is able to provide a very good insulation when it comes to any airborne sound. Meaning, if you build a wall that thick with cavity or empty air in between, there's two layer, then any sound that's trying to travel through this wall is greatly reduced if you're at the other side. But if you were to reduce it, let's say you just have a single layer wall, then you find that this wall is not able to insulate or reduce the transmission of any sound against it, as well as the previous dispersed wall. And then finally, you have other material, and then you have your plaster. So this table is done through experiment, meaning how they get this SRI is through experiment. So all of this is actually constructed, and then experiment is done where sound is generated and measured from point A before and point B after the wall, and then they are recorded. So it's not only just one, a few experiment is done, and an average value of sound is recorded here as a reference for studying. So this is a case for wall and also for window. So for window, based on this, we know that if we were to construct a very, very thick component in between us and the source of the sound, we will actually be able to reduce the transmission of sound. So with that, we can actually make a very, very quiet room. So when we are in a room with this sort of construction material around us, then we will have a very good or quiet room, which is not able to transfer a lot of sound from the outside to the inside. So this is how construction material. This is done on basic construction material which we use all around the world. So it's beneficial to know that how we build a wall, and according to requirement, if it's a very noisy environment, then we should build a thicker configuration to ensure that the quality of life for the resident or anyone who buy the house, let's say if you're living next to a highway, it's not very bad. Because if you have a very, very good composition or build up of the wall, meaning you have a double layer with cavity in the middle wall, as opposed to just a 50 mm dense concrete that's not able to reduce so much of the transmission of the sound, then that's where the difference come about. So in Malaysia, usually what we have will be something like this, 100 millimeter brickwork. So we are, I mean, if you were to have opportunity to go overseas or you are interested, you can always study the plan, meaning our drawing plan. So in our drawing plan in Malaysia, typically we just adopt 100 millimeter brickwork. But when it goes to overseas, so there's actually a difference. So you'll see that some country they will adopt up to 255 millimeter brick. So why is there this sort of differences? So it's not because they are rich. So it's because, let's say for example, Australia or UK. So what's the difference between their country and our country? So they have 4 seasons. So when that happens, then they will need to consider cold weather and hot weather. So in Malaysia, we don't really have 4 seasons because we are a tropical country. So only 100 will be good enough. But when it comes to cold country, then having this thin layer of wall doesn't really justify a very good quality of life lah. Due to, if your wall is too thin, then when the cold weather hits your building, then you lose a lot of heat energy. So you waste a lot of electrical energy trying to heat your housing. So that's why if you were to ever be given an opportunity, you'll notice that there is different configuration based on different needs of a building or a country or based on situation. So when it comes to residential building in Malaysia, you all just be stuck here lah, 100 mm. But when it comes to commercial, then we have some sort of standard that needs to be applied. Okay, so we might have a 255 millimeter wall if it's required, but usually we only have up to this level. So there's 4 factors that is the principle behind insulation. So we have heaviness, isolation, completeness, and flexibility. So when it comes to heaviness, here it mentions heavyweight structure with high mass transmit less energy than lightweight structure. So why does these factors explain it this way? So going back to the fundamental of sound, we know that how sound is being transmitted is all about movement of particles. So when you hit a heavy object, how does this sound energy get transferred to the other side? So sound is all movement on the air if it's airborne sound being generated. So when it hits a structure, for this airborne sound to be transmitted to the other side of the wall, they will actually need to transfer their energy through the structure, meaning they actually have to vibrate on the structure. They will have to transfer from a gaseous state to the solid state and then transfer back into a airborne state so that it can be transmitted to us. So all of this transfer of energy is where the insulation comes about. So if you have a very heavy structure that is not easily resonating or vibrating, then you have a very good insulation material. So this shows that if the object is very dense, then the energy required to transfer or to cause this sort of vibration is very high. So when that happens, you will not hear any sound because all the sound is being used up by the material itself, is absorbed by the material. So this is what it means by heaviness. So if it's a light structure, based on how the principle of sound is being transmitted, which is movement, vibration, then this structure will vibrate with it, like what you see with some building. So all this movement of the building, it doesn't mean it comes from a source where this sort of movement is able to generate sound, but it's more towards the vibration lah. So if it's a sound generating vibration, we call it a sound. If not, then it's just a resonant. Okay, next is isolation. So discontinuity of construction. So for example, we have this, the first configuration of the wall, which is we have a brick layer, we have a cavity, which is just a void, and then we have another brick layer. So this is what it means by discontinuity. If you have different layer of object in between you and the source of sound, then the transfer of the requirement for the energy to go through all this layer will be very high, because they will need to be converted. The transfer of energy needs to be converted from air to solid, to air to solid again, and then to air. So this isolation of, or discontinuity of the construction is very effective in reducing the transmission of sound. So next one, we have completeness. So when it comes to completeness, it means you have a solid wall. So there's no gap in between. So if your structure, if the object between you and the source of sound, if there's a hole in that layer, then that means that that layer is not really helping you in insulating the sound. So you want to have a wall that do not have any air gap. And then next you have your flexibility lah. So no lowering of insulation to resonant or coincident. So yeah, not much can be said about this lah. Okay, so this is an example of isolation. So you have a layer of window here, you can have a airspace, and then you have a window here. So when it comes to window and brickwork, this window actually have a lower sound reduction index as compared to a brick wall. So why is it? Because all the material is made of lah. So glass is not the most dense material, is easily breakable, but to be able to reduce the sound, to give the best sound insulation, we want to install some sort of configuration like this, where we have a rubber or resilient mount, where we mount onto it so that the noise being emitted doesn't go through the joint, and they have to go through this sort of configuration and layer. So this is what makes a good sound insulation for a building. Okay, so coming next to this formula. So in our construction, this table, based on this table, we know that our typical wall is not just made of only one material. We have a composite material, meaning just for a single face of our wall, we can have different components. So all these components, we can use this composite material to work it out what is the SRI for this particular face of the wall or partition. So this is a formula that we can use. And then you're given that T is a transmission coefficient, and we'll be using back this formula, which is the SRI. Okay, so this is basic. This formula, if I'm not mistaken, it is not given but this is just a very basic composite formula, meaning to get the average of all the value in an area. This is a typical formula used. Okay, example of how the first formula can be applied. You have your example 6, which is a SRI. So a wall transmits 1% of sound energy incident upon the wall at a given frequency. So you are to calculate the sound reduction index R of the wall at this frequency. So you're given, you assume that the incident sound energy is 100, and based on this example, you let it be 1%, or you just give it 1 based on the question given. So based on that, you can work out that your T is equals to 0.01, which is 1% of the sound energy. And then if you were to work out the formula, you work out that the SRI is 20 dB. So this is just an example to show that what is the SRI of this wall at this frequency without any additional information. So for just being given this 1%, you'll be able to work out that the wall have a sound reduction index of 20 decibel. Just an example of how a formula can be used. Okay, so example 7 will make use of this composite partition. So we'll be given a wall area which have a window, and then also which has only a wall and a window. So there's only two components. Okay, you'll be given the area for the wall, which is 10 meters square, and then the area for the window, which is 2 meters square. And the SRI for both the wall, which is a brick wall, is 50 decibel, and then for the window, 18 decibel. And then based on this information, you have to calculate what is the overall sound reduction index. So you have to use the formula which is given here. So if not mistaken, this should be given to you also. Let me do a quick check. Formula sheet. Yeah, so it's given to you here also, which is this 6. Okay, so the composite formula is also given to you. Okay, so you have all of this. So to solve this question, you want to find out what is the transmission coefficient for brickwork and window. So you have to repeat 2 times. So based on the example given, you know that your wall area is 10 meters square, and then your window area is 2 meters square. So a wall is 10 meter, and then within this 10 meter square, you have your window. So you need to minus it out. So based on that, you get 8 meters square, which is your brickwork, and then you have your window, which is 2 meters square. So with that, you want to solve what is the transmission coefficient for your brickwork. So using this formula, SRI equals to 10 log 1 over T, you can put in the 50 decibel, which is the sound reduction index for your brickwork here. Put it in, and you can solve this equation. and then you end up with the coefficient equals to 10 to the power of negative 5. So do try it out. We still have some time. I'll be around later on. After this, I will end the lecture with this example. And then if you got any problem, then do let me know, and and we can I can help you try to figure it out lah. So if you haven't uh, try pressing logarithm in your calculator before, you can try it later on after I end this example. So you work this out. So here the 10 is moved over, that's why you have a 5. And then when you move your logarithm to here, then you'll be using the rule of logarithm lah. So you move your logarithm to the other side of the equation, then this will be to the power of 5. So you'll be 10 to the power of 5. You inverse it, and then you'll get 10 to the power of negative 5. So you get your coefficient, the transmission coefficient for your brickwork. So for window, you have to repeat this step again. So here, this is not shown. Let me see. Yeah, so here it's shown. Okay. So here is shown. I think I got additional. Yeah. Okay, so here you have 18 equals to 10 log 1 over T2. So you want to find out what is the T2 transmission coefficient for the window. So you work it out, the transmission coefficient for the window is 1.585 times 10 to the power of negative 2. So for your calculation, when it comes to calculation, if you give me 2 decimal point, that will be good enough lah. You don't have to go to 3 or 4. So just 2. If you want the question or the answer to be more accurate, you can go for 3 or 4, but you don't have to go more than that lah. Okay, so getting the answer, as long as the step is correct, if your answer is different a bit, as long as you have up to about 2 decimal point, then I will just mark it correct. Okay, just so you guys know. Okay, so you work out here, you get the transmission coefficient for your brickwork and then your window. Then you have the transmission coefficient for both of your component. So with that, you can use your composite formula, which is this, and then you just plug them in and multiply them with their area, where the bottom is you just add them together, and you get the transmission coefficient for these two material based on this value. And after that, you want to get what is the SRI, the sound reduction index, for this composite wall, which is the brickwork and the window. So you plug in the transmission coefficient into the formula and you solve it, you'll be able to get that this composite wall made out of brickwork and window, which have different SRI with different area, you'll be able to obtain a sound reduction index of 25 decibel. So you have to follow through this sort of work method lah, to get the answer for this example 7. Okay, so I think I stop here lah. You have enough information.